So as we discussed earlier that in information extraction we have primarily two kinds of subtasks, in which one task is the named entity recognition and another task is relation extraction. So what is relation extraction? Relation extraction is actually figuring out or extracting the relationships between the entities present in the text, right? So if we have some text like International Business Machine Corporation, IBM, or the company was incorporated in the state of New York on some date as the computing, tabulating, recording company, CTR, and something like this. We have this text, so we need to extract some kind of complex relations between the entities. So we see that this is an organization, this is the location, this is the date, and this is again a kind of another named entity which has been specified as the original name, and this can be also be referred to as org, right? So we see here that we have these entities that can be identified through the task of named entity recognition. Right now we need to further go into the complexity of the task and identify the relationships between these entities present in a piece of text. So we can identify the relation is what we can identify the founding year, we can identify the founding location, right? So the relation extraction task could be reduced to a very simple task of just extracting the triplets in which we have one is the relation and two are the entities, right? So this is founding year is the relationship and IBM is one entity and this 1911 is another entity, right? So we could have this kind of triplet that we need to identify in the relation extraction task, right? So this is actually triplet form is very suitable for relation extraction because in lot of data that is present over the internet we could easily acquire these triplets. So if we go for a Wikipedia article, from that article we can easily see that lot of triplets can be acquired. So Stanford is equivalent to the Leyland Stanford Junior University. So we have this relationship. The Stanford located in California, we have this relationship. So these kind of Stanford is a research university, Stanford located near. So we see that different kind of relationships in the form of triplets can be acquired from the data that is present in Wikipedia, and Wikipedia is a very rich and vast resource for text, right? So why do we do the relation extraction? Because we can actually augment the current knowledge bases, like we can augment the WordNet, we can augment the Freebase or DBpedia. That means we can add up more information, more kind of the information that is itself present there, we can add up similar kind of information there, and it is quite helpful in question answering, because the question answering is actually in the form of the named entities, and the questions are in the form of relationships, and answers are in the form of named entities. So and a question can be easily built on using a one entity, single entity, and a relationship, right? And the answer could be another relationship, or we can have simply a relationship as the questions, and then we can generate the answers in the form of named entities. So these are also in the form of triplets. We see that this is the relationship, this is the entity 1, and this is the entity 2, right? So we are specifying here one entity and we are expecting the answer in the form of another entity. So this is also the unknown, this is also unknown. Here both the cases are unknown, right? So this relation extraction could also be creating some kind of structured database like this, So automated content extraction was a relation extraction task that was introduced in 2011, and this task actually introduced a lot of relationships between the different entities. So we had six principal entities like personal with social, then physical relationships, and then general affiliation and part whole and organization affiliation and artifact, and these were further fine grained into the smaller subsets of personal relation. That means there is something family relationship, business relationship, and some in case of organization affiliation we have the subsets as founder or owner or member or employed or student, etc., right? So these are actually the blueprint for which we can use these as a blueprint for identifying some kind of relations from a given text, right? So we will generally use these the relations present in these standard relation extraction tasks. So what were those relationships that were present or that are specified? So in physical located we have a person and a geographical location, and we have the relationship as like was in. Similarly in organization we have the relationship the parent company of. So these are some kind of examples of the relation of this automated content extraction task. Apart from this automated content extraction task, we have for medical relations we have a unified medical language system, UMLS. So this UMLS is a very standard source of medical or biomedical named entities and their relations. So this is a rich source of rich and standard source for biomedical and clinical named entities and relations. Okay, so an injury disrupts a physiological function. Pharmacological substance causes some pathological function, like a drug may cause some kind of side effect. Similarly, a pharmacological substance treats some pathological function, is like a drug treats some kind of disease. So these are kind of examples in which these are the relationships that are present in UMLS. Okay, so we can use this UMLS again to train some kind of classifier and all. Similarly, we can also so we see here that we can use the data set or the text from the automated content extraction task. We could use the text of UMLS. Similarly, we can derive the data set for the relation extraction from the Wikipedia. And Wikipedia, we know that in each of the article of Wikipedia we have info box on the top right corner. So this info box contains the information about that entity, and from this info box we can derive the relations also. We see that the Stanford is location is present with this location, right? So this article is about Stanford and the location is California and the relationship is location, right? Similarly, we can extract different kinds of relationships, like this John L. Hennessy and this president, and we know that this info box belongs to the Stanford University, right? So we can extract such kind of data set from the Wikipedia info boxes. Then we have the ontological relations that are present in the thesaurus based encyclopedia like WordNet. So we can utilize WordNet also, and whatever relationships that we studied earlier, we can use those relationships and then derive a data set from WordNet also. Like San Francisco is an instance of city, and giraffe is a ruminant, is a ungulate, is a mammal, is a vertebrate, is an animal. So we saw that WordNet has these kind of hierarchical relationships which we can use for relation extraction task. So how to build a relation extractor is, we all know in general, in principle, whatever task we studied, we saw that we could solve that task with the help of primarily three approaches. One approach is the handwritten patterns, second approach is the supervised, third approach is the semi-supervised. Right, so the handwritten patterns work quite well when we have a small amount of data and the rules don't change with time, right? But when we have large amount of data, we see that it is not very domain specific and the rules are changing with time, we switch over to the supervised machine learning algorithms. But when we see that we do not have enough data and the data is again very dynamic in nature, the rules are changing with time, we cannot design the rules, and we don't have the data even, then we apply the semi-supervised algorithms. With the help of these semi-supervised algorithms, we regenerate the data from a small set of data, right? So in this relation extraction, we will be covering only the handwritten part and the supervised learning part. We won't be covering this semi-supervised or unsupervised. So if any person wishes to go through this topic, he can go through the book. So we derive some kind of relations from the text, and then we write the rules for that relation, right? For in this text, suppose if we are extracting rules for is a relation, right, and we have this text: agar is a substance prepared from the mixture of red algae such as Gelidium for laboratory or industrial use, right? So an algorithm that was or the methodology that was proposed by Hurst in 1992, it says that you can generally put up the question that what does Gelidium mean. So in this is a relationship, we identify that Gelidium is a named entity, right? Then you can put up a question, what does that mean, right? So we see that there is again some kind of expression or a phrase or a simple word that is present preceding or succeeding Gelidium, that this is the such as, right? So with the help of which we can identify that Gelidium is a red algae, right? So we can identify large number of such patterns with the help of these propositions or these phrases like such as and like or other and other, including, especially. So these are all are relating to the is these all are actually providing a is a relationship, right? So similarly we can identify lots of relationships, like so such y as we can have different kind of patterns, x and other y, x or other y, x such as y, and these are the examples. These are the different kind of relations is a relations, and these we can see an example, the bolute such as Bambaran and Dang, and this is taken some kind of maybe some English corpus. Okay, so now we can again move on to some kind of richer relations that are more practical in nature and more applicable in nature, and which we did which are also helpful with the help of named entity recognition task. So the popular entities that are in named entity recognition task are location, organization, person, and in case of medical data, these are drugs and diseases. So the general data sets that are present with the named entity recognition task can be easily converted into the relation abstraction data sets. Right, so whatever on whatever data we can apply the relation, we can apply the named entity recognition, we can also apply the relation extraction, and these are quite helpful, because once we identify the named entities in a task, the further extension of the work is to identify the relationships. Right, so popularly the relations that are present with these popular named entities are located in founded, close, and much other relations. Right, so these are some examples. So we could have similar as we studied just now, that person is on the position of an organization. So we see that now we are moving on to much more richer relations, like a person named or appointed or chosen as a person proposition for a position. So we see here that these are the named entities. These are the named entities. And there is some kind of this is also named entity, so there is some kind of relationship present here. This is a relation that is present. Similarly, right, so depending upon the type of text we are using, we can derive several kind of relations, right? And then what we can do is that we can build on handwritten rules for these relations. Right, we can write the rules for these relations. So how do we write rules? Writing rules is a simple kind of if else code. If this is true, the condition that we are having this kind of first kind of relation expression, then it is this particular relation, then we define that it is this relation. Right, so if it is this rule, some subset of this relation, then we again go for this expression evaluation, regular expression evaluation, and then we say that it is this particular kind of relation. So in this way we can write if else kind of decision kind of code, which can decide while parsing the text, it can decide whatever relationships are present in that text. So prerequisite is that we must know what are the named entities present in that text. Right, so we all know that these human patterns are of very high precision and are very specific to domains. So if there is a kind of say tourism data, then very limited amount of tourism, for a very limited amount of tourism data, the algorithm will work well. That this tourism data cannot be expanded to some other kind of say educational data or some other kind of data. Right, so it cannot be converted into a generic algorithm, but as in machine learning algorithm, we can expand the data and we can move on to a generic kind of classifier. Right, so we can have a different we can club all such kind of categories into a single category, and a single classifier can be not very much accurately, but it can obviously with some reasonable accuracy, it can handle all the relations altogether. Right, so why these are of high precision? Because whatever the algorithm is predicting, it is actually predicting among among all the instances, it will be mostly predicting the correct ones. But we are rather interested in recall, which states that whatever data is whatever data is predicted, among that most of them must be the correct ones, right? So often these handwritten patterns are of low recall, because whenever some new kind of data is there, they are not able to predict well, right? But overall, if we see, we mix both the new and old, and then we predict, and then we see the overall result, then we get that the precision is high but the recall is low, right? Because the precision is actually calculated from the overall data, and the recall is calculated from the predicted data. So we move on to the supervised machine learning algorithms. So again, there is a general principle, the same principle that we need to apply. We choose the set of relations we would like to extract. From those relations, we need to again identify what are the named entities. Then we apply the same machine learning framework here. We choose the corpus, we label the named entities in the corpus, and then we hand label the relationships. Again, we label the relationships. Now in case of named entity recognition, the labels were the named entities, but in relation extraction, the labels are the relations, and then we do the training and all, right? So if we are doing a relation extraction, so we first specify what is the relation, right? So we need to have these set of standard relations, and for a particular relation, then so suppose we are having this text, and then we are fixing some kind of relation. So for this relation, we can identify whether it is a citizen or family or subsidiary. We can fix any of these relationships, and for this particular relationship, we can prepare the data set, right? So what we do is that for a particular text, we find the pair of named entities, and then we see that if these two named entities are related, and then we see that if these could be put into the data set. So what we do is that we have this kind of we prepare this kind of table, in which we have the named entity 1, we have the named entity 2, and then we see that whatever kind of relationship can be seen present in these standard 17 relations. So this is the relation, and these can be treated as named entities, are treated as features, and these relations are treated as labels. Right, so once we get this kind of tabular from some data set, we can proceed on to apply the feature extraction. So again, we have the common bag of words we can apply, right? So what is the bag of words? Bag of words is again the collection of all the words that are present in the named entities. So American, Airlines, Tim Wagner separately, as well as so both the bigrams and word bag of words is included in this context. So this part is actually only the bag of words. Sorry, this part is only the bag of words. This is the BOW, and this is the bigram part, and collectively both are clubbed into a single feature vector. These are the bigrams, right? Similarly, we can have the context also, we can get it involved into the feature set. So we can have preceding and succeeding words. Preceding, that is -1, and succeeding tokens, +1 tokens, and we can increase the window size depending upon the type of text we are using. So we can increase or decrease the size up to some say 2, 3 or 4, something like that, right? So we can have also so here we have mentioned that we can have bag of words. So some kind of simpler representation of the feature vector is that just we are having the head words in in the features, right? So if there are two entities M1 and M2, so the head word is actually the more common word that is present in the entity, or that is more, more spoken word. So the airlines, Wagner, these are the two head words, and we could also include a combination, right? So this is a very simpler representation, but instead of moving on to the more complex representation, we could apply the bag of words, and we could also apply the bag of words or bigrams for a set of words that are present between the two entities, right? So this is the set of words that is present, the collection of words or the sequence of words that is present between the two entities. So we can have the set of words and then generate the bag of words or bigrams or both for such, right? So we see that we can have different kind of features, and apart from these also intuitively we can think upon, depending upon the domain and the problem, we can think of different kind of features, right? So now we can have more complex set of features, right? So we see here that from a syntactic parse tree, we can see that what is the constituent path from one component to another, and then we can see that whether in that path, moving from one entity to another, from one mention to another, whether we are going upwards in the tree or we are going downwards to the tree. So since we have not covered this in the syntactic parsing, we have not covered this, so I'm not discussing this in more details, but we can have simpler kind of features. One more feature that is here specified is that we can have the kind of, we have that the M1 and M2 is also referred to as some other reference, like it is referred by a nominal, it is referred by a pronoun, like. So we can also use these kind of features as well if we see that these are present in some span of text, right? So we can also use some kind of gazetteers or some kind of list from a source. So gazetteer is actually a standard set of list, like in case of geographical named entities, we can specify that all the list of cities or all the list of countries and states. So we could say that this is a gazetteer, and gazetteer acts as a kind of additional information, and it also acts as a kind of lookup table. So we see that if some kind of gazetteer is present in that data as of these named entities as a feature, so that could be used as an additional feature. So if the feature or that entity is present in the gazetteer, so that is again a kind of positive and more kind of additional information that could be utilized. This could be as well utilized in the named entity recognition task also, right? So we see that we have different kind of features that we can utilize in the relation extraction task. So some are very generic kind of entity based features, like the name of the entities, the concatenation of the entities, or the word based features, the words that are surrounding the entities, like bag of words, of the context bag of words, or of the words present between the entities, or bigrams and trigrams of these words. And we can have more kind of linguistic features that can be derived from the syntactic dependency trees that can be generated for a given sentence, right? So we did not cover this in our course. So now once we get the features, we know that we need to just train a kind of simple classifier, right? And then we can calculate or evaluate that classifier. So in summary, we can say that these machine learning algorithms do have very high frequency when we have enough amount of data and enough amount of hand labeled data. So hand labeled data is actually labeled by hand, and we do not employ any kind of automatic mechanism to label that data. But hand labeling such kind of data is very expensive, so we have the kind of another class of algorithms that are semi supervised algorithms.